Good afternoon, and welcome back to the Toolkit training program as far as programs to be used by distribution engineers and designers. Okay, well, today we're going to talk about transformer connections now. Last time we talked about the single-phase transformer. Today we're going to talk about three-phase transformers or three-phase transformer connections. And the one we're going to concentrate on is the closed delta bank transformer connection. So let's get started. I'll go ahead on and click on the program button. Okay. Well, now on the screen what you're looking at is a three-phase four-wire closed delta secondary transformer connection diagram. Alright. I said that really fast, but basically I was just reading this up here. And over here in the right top corner you see two delta symbols, a delta for the primary and a delta symbol for the secondary. And basically what it represents is the way the transformers are electrically connected to get to each other. The ones we're going to concentrate on is the secondary, because this is where the customer picks up his load from. Okay. And so we're going to concentrate on the secondary delta triangle here. Each leg of the triangle represents the secondary coil of the individual transformer up on the pole that it's connected to. So in other words, I have 1, 2, 3 sides to the triangle. That means I have 3 transformers, secondary coils up on the pole. So each transformer on the pole has a primary winding and a secondary winding. So that's 3 transformers on the pole, 3 primary windings and 3 secondary windings. Now if we look at the bigger picture here, like I said, I'm going to concentrate mostly on the secondary scenario as far as the transformer is concerned, or transformers are concerned. And that's the way we're going to determine the loads on this particular transformer bank. Well, you might ask, well, what is a bank? Well, a bank of transformers is basically 2 or more transformers connected together to provide a certain voltage to a customer or multiple customers. In this particular case, we said we're going to start with a delta scenario, and what typically is provided to the customer with a delta transformer bank like this is 120 240 volt single phase and 240 volts 3-phase. I mentioned that this said closed delta. That means that all the way around the connections there's nothing missing. Everything is there. You go from one bushing to another bushing, through the transformer to another bushing, through a transformer, through another bushing, and so forth. So it's all looped up through that delta triangle there. The next program that I release, or the next video, is going to really talk about what we call an open delta. This is a closed delta. The other one will be an open delta. And it's just like it sounds, is that I won't have a closed triangle. I'll have a triangle with a part missing, and I'll explain that later on. Okay. Okay. So this is the closed delta scenario on the secondary side of the transformer bank up on the pole. There's 3 transformers up on the pole, and what you'll notice when you're riding around different cities, place to place, whatever, you'll see 3 transformers up on the pole. And the one in the middle a lot of times will be quite a bit larger than the other 2 on the outside. And I'm going to explain to you what the reason is for that. But that normally is a telltale sign that this is a delta connected transformer bank on the secondary side. Well, let's take a look at it. And since I've already told you that we'll actually be providing a customer the voltage from this particular bank, he'll be able to get 240 volt 3-phase, and he'll be able to get 120 240 volt single phase. So let's talk about the 3-phase scenario first. Okay. There's 3 lines coming away from this bank over to the customer service that are required to provide 3-phase power to the customer. Line number 1, line number 2, and line number 3. So if I wanted to give this customer power to provide power to his pump or whatever, that's 3-phase, all I really need to do is run 3 wires over to that service. And this pump or motor load, whatever he has, 3-phase, will be balanced. And when I say balanced, that each one of these wires that I'm taking over will have the same amount of current flowing through them. So that's balanced as far as electrical nomenclature is concerned. Alright, so let's say that the customer comes to us and he says that he wants to have power to a 7.5 horsepower motor that he's installing on his property. Okay, he's told me it's going to be 7.5 horsepower, and I'm telling him that, well, the voltage that I'm going to give to you or supply you will be 240 volts or 230 volts, 3-phase. So let's take a look at that. Let me go back to the master menu here. Okay, this is a motor current table that I've thrown in, that people can use to quickly come up with amperage running current for a particular size motor. You notice 7.5 horsepower here at 200 volts is 25 amps, at 230 volts is 22 amps. So you can see as the voltage goes up, the amperage goes down. So at 240 volts, it's going to be a little less than 22 amps. But for this particular example, I'm just going to use the 22 as if it's 240 volts being served to the customer. Okay? So I'm going to go back to the master menu here and go back over to our closed delta. So the customer said he has a 7.5 horsepower pump or motor, and that's going to be drawing 22 amps. And the voltage that he's going to get is basically 240 volts, 3-phase. Each one of these lines, between this line and this line, there is a voltage across it, and that's called a line-to-line voltage. And also between this line and line number 1, the same 240 volt voltage is being applied, and then between the 2 outside lines. So you'll notice here I have E line to line and E line to neutral and E line to line here. So that's representing what's being supplied by the conductors going over to the customer's service. Okay, so he has a 3-phase pump. It's going to be 240 volts, and we're going to call it 22 amps, just like shown on the chart. And then once we've got that information, we can determine on these 3 transformers how much load is being applied to each one of them from his, or is being drawn from each one from the 7.5 horsepower motor. So I've already put in the amperage on the motor, the voltage of the motor, and let's see what it draws. I hope they are. Okay. Alright, well, over here in the bottom, what it has here is a grid table here that shows each transformer 1, 2, and 3. 1, 2, and 3. It says single phase load on transformer 1 is 0, transformer 2 is 0, and 3. And that's true, because what we did, we only told the customer where it'd be serving his his 3-phase pump, which is what he gave us information on. So therefore, what it turns out to be is that the load on each transformer in this delta connection here turns out to be 3 kVA on each transformer, and it's all 3-phase load, because that's where we started off with here. Okay, so keep in mind that when you run in 3-phase from a delta configuration, as far as like shown here, the amperages and the load should be the same as far as the three-phase load is concerned. So 22 amps, 22 amps, 22 amps. That's the load. It should be the same for each one of those three wires, line 1, line 2, and line 3. Alright? Okay. Now, you might ask the question, what happens if I'm taking a reading and one of them is extremely high? Well, let me back off on that for a second. I think I'm going to wait before I bring that up because I'm really getting a little ahead of myself. Okay, so anyway, that's the three-phase, three-wire service to that particular customer. Alright, and it's a balance, and it's telling me now I got 3 kVA on each transformer that's being served. Alright, now you notice here I said combination three-phase and single-phase service. Oh, well, we talked about the three-phase service real quick. The single-phase service, well, single-phase service is exactly what it says. We can take one wire to the neutral position. So a hot wire to the neutral position is going to provide a certain voltage, and a hot wire, the other hot wire to the neutral position will provide a voltage also. And that voltage that we get in line to neutral is 120 volts. Okay, so I have 120 volts line to neutral here. But if I have 120 volts from here to here, and I also have 120 volts from here to here, so 120 volts across from hot line to a neutral, hot line to a neutral is what I have shown here. But if I go from this hot line to the neutral, it doesn't turn out to be 120 volts. It turns out to be 207, and most common people nomenclature used for this is just 208, and you usually call it a high leg, a stinger leg, a power leg, whatever, whatever's normal for your company, but it is a high leg, okay, as far as I'm concerned. And that is an oddball voltage that you don't use for your single phase load, because you're usually using 120 volts as your phase to ground voltage when you have a 120 240 volt delta connected transformer bank. So let's do this. Let's add some single phase load to the customer's demand here. He's got three phase. He's got 3 kVA 3 phase per transformer. We've already shown this as to what he has on each one of the transformers. Now we're going to add some single phase, and that single phase is going to be 120 240 volt single phase, and we're going to add this based on what he's given us as far as his load information, and it turns out that what he's provided to us is that instead of having just 22 amps on line 1, he's going to give us another 30 amps of single phase load to be connected to line 1. That's going to be from line 1 to neutral. So he says I have 30 amps of single phase, so that turns out to be added on top of the 22 there. Excuse me. It'll be 52 amps. So 52 amps there, and let's say that it's balanced off. In other words, he would have 52 amps on this particular leg and 52 amps on that leg. Let's say that it's balanced off like that. Alright, well, let's see what happens when we ask for the calculations. Okay, well, we've got the calculations alright, and now you see that we have 52 amps now shown. But look at the transformer now. Transformer 2 and 3 shows a load of 5.4, and transformer number 1 shows a load of 7.9. Okay, so now what I have done is that we have the three-phase load that we computed earlier based on the 22 amps for the 7.5 horsepower motor, Now we have the single phase load based on the additional 30 amps that we have on line 1 and line 2. Okay, so that single phase load is being distributed over all 3 transformers, and this is the total load of the transformer bank itself. So now if I was to decide this was a brand new setup and I needed to install transformers in the field for this particular location, I would probably call for 2 5s and a 10 kVA transformer to be installed on that pole in a delta configuration. Pretty straightforward. Well, let's see what happens if he gave us additional single phase load and he said instead of being 30-30 on each one and 1 and 2, it turns out to be, let's say, 30 again. So I'm not 30, let's say yeah, we can do that. So let's leave it at 52, and then instead of having 22 with 30, let's say 22 with 40, so that'll come up to 62. And let's see what happens here. Okay, so now the loads have been redistributed again over the transformer bank. It's a little bit higher, but you'll notice now that there is an amperage current running in the neutral wire. Now we're taking advantage of the neutral electrically because there's an imbalance between line 1 and line 2. Keep in mind it's the same thing we had on the single phase transformer video before, that the neutral current basically is the difference between the 2 hot legs off of the transformer bank, off of the transformer that has a center tap ground. So this takes care of the differential between the 62 and 52. That difference is 10, and that's what would be flowing in a neutral current itself, in a neutral line itself. So basically that's what happens with the delta connected transformer bank. I can actually have 3-phase and single phase load connected to this connected to this customer service coming from this transformer bank. All you really need to know is what that load is that the customer is going to be asking for or going to be drawing away from that particular bank. And once you determine that, then you can see what happens once everything is added up together. This is pretty quick, but anyhow, it gives you an idea of how the delta bank works, the closed delta bank works. To keep in mind two important things. There's no single phase load connected to the high leg to ground, and the other scenario that is a taboo scenario is that the high leg should never be greater than the other 2 legs on the transformer bank. In other words, this number has to always be less than or equal to line 1 and line 2. Okay, if not, you have a problem. So anyway, that's it. I do have a little help note here, and it's straight from a GE manual. Most people have probably seen a little GE distribution manual, that little handbook that they put out. That's where this note comes into play, and it talks about the loading on the bank itself. Alright. So, okay, well, that should do it. And as usual, if you have any questions or concerns about it, feel free to contact me, and we can make arrangements to work things out with you. Okay? All right. Thanks a lot for your time.